Hi everyone, uh, my name is Theepan and I'm going to present about evaluation and optimization of AC losses in a fully superconducting machine for offshore wind turbine. Uh, Even though my presentation is focused on offshore wind turbine, but since I am working on two projects, one is electric propulsion, so I will highlight some of the comparison of AC losses in two different design schemes that I'm working on. So me working Noah Sag is an undergrad, and then Dong-Soo Lee is a postdoc, and we are working with Professor Hirbahar, and he's our supervisor. First, I would like to focus on why we are focusing on like wind turbine and why the superconducting machines are very promising for this application. As you can see this in this plot over the years that the capacity of the wind turbine installed is keep increasing from 2 to 3 megawatt. From now it's coming around like 8, 10. So it's forecasted in eventually it will go to 10, 12 megawatt range. Why we are going for a bigger wind turbine is for this reason. One is that capture more energy. Like if you have a 10, 15 megawatt, then we can capture more energy and increase the capacity factor in the partial loads and also reduce levelized cost of energy. I will go over it in the next slide. What does that mean? But if you look at a general equation for a machine, so this is the output power for a general machine. So what we have here is some constant multiplied with the volume of the machine, and the magnetic loading of the machine, and the electrical loading of the machine, and the speed of the machine. So, but if we want to increase the power of a machine to like 15 megawatt, obviously we need to increase one of these parameters. We have to go for a bigger machine, or we have to increase the magnetic loading, need to put stronger magnets, or increase the field, air gap field, or we have to increase the electrical loading, or maybe armature current, or we have to increase the speed of the motor. So we have to increase the speed of the generator. So, but can we go for a large machine? No, I mean we have some constraint. For example, if you want to build a big machine, you have to transport the machine to the installation site. That's have a typical constraint because the roads widths are 4 meters, or we don't design more than 4.5 meter diameter machines. So we have a, and then you go for a, I mean when the volume go high, the weight go high. So we were talking about offshore wind turbines, so that then the tower cost will increase. And then if you go for increasing magnetic loading, then the thermal limits will come, the hysteresis losses and the eddy current losses will increase. And if you go for like permanent magnet machines, these are costly. Magnets are very costly, so the cost will increase. And if you increase the electrical loading, then we will increase the resistive loss in the conductor. Then we have to add more cooling powers. And if you increase the speed, then we have to put gearboxes, and we need to deal with all those mechanical losses. So obviously now that those are the constraints that's limiting to go for a bigger wind turbine. So what is the solution for this one is the superconducting technologies. Why this is cool? Because we have zero resistance at cryogenic temperature. What does that mean? We can push more current to go for a higher field in the field winding, and we can push more current in the armature to increase the electrical loading. So what does that mean?
What is the cryogenic temperature?
Cryogenic mean like very low temperature, like 20 to like 70 Kelvin, 80 Kelvin. So that's is very low temperature. That's we need to work around.
And what is the significance of that? Why
because it's not, I mean, achieving cryogenic temperature is a challenging task, because we are talking about very low temperature. So we need to use the coolants like liquid helium, liquid hydrogen. So that's why it's quite challenge. So what does this mean is that without increasing the volume or speed of the machine, but by increasing the electrical and magnetic loading, we can go for a higher power machine. So that's the idea of superconducting machines. For example, like air gap flux density, theoretically we can go up to 10 Tesla. Typical machines will have like less than 1 Tesla. And the current density we can go up to 200 amperes per millimeter square. So normally the conventional machine will have 7, 8, or even less than that. So these are the benefits that why we need to go for a fully superconducting machines. When you take superconducting machine, there are two kind of machines. One is partially superconducting, the fully superconducting. The partial superconducting mean we only use field coil as a superconductors. We use the conventional copper coils as the armature winding. So that is the partial, and fully mean we will replace the field winding as well as the armature winding. So there are two kind of designs that I put into here. So one is the conventional design with iron core or iron shell. The other one is called we working with the active shield design. So we eliminate the iron core from the design and we put some active shield coils around the machine to contain the flux within the machine. So in the conventional design, partially superconducting is already explored very well, tested and built. For example, GE built one of these machines for winter. And these active shield machines just studied in UIUC, proposed by our university, and we have only the design, we never built or tested this one. The fully superconducting, nobody built any fully superconducting machine so far because handling the armature current and the associated losses are quite challenging, and I will go over it. What are the challenges we have? We will go, the cost will increase, and the AC losses in the armature, that's the main challenge to go for a fully superconducting machine. These losses are not the resistive losses because the resistance is zero, but we will have losses called AC losses, and that's going to be a quite challenge to go for a fully superconducting machine. And then we need to cool down the whole machine, and then we have to design the mechanical machine, and then how do we going to put it in a wind turbine. So these are the challenges of fully superconducting machine. So this is a comparison pics I got from AML. You can see that when you go for a conventional with gearbox around 500 tons, you can see the size, and then permanent magnet, and then partially superconducting and fully superconducting is the size comparisons to show that where we are going. So these are the benefit, like we can go for a higher power, and then the efficiency will go high because we don't have any resistive losses or eddy current losses, those losses, and core losses. And then we can reduce the weight by significantly, and then we can reduce the cost also because these superconductors are, for example, if you choose MgB2 conductors, the cost is very low. And then reduction in maintenance cost and efficient energy capturing capability of partial loads. This all bring to a reduced levelized cost of energy. What does that mean? That if you put all the cost associated with the operation and you divide by the total energy produced, this will be very low compared to conventional machines. So these are the two proposed machines we are studying. One is called, this is our proposed design. We eliminate the core from the machine. And this one is the conventional machine which have the iron core inside in the outside. So we were focusing on 10 megawatt, and we were studying different pole counts, and because to understand which one is best for this application. And our speed is a direct drive 10 RPM, and we use MgB2 superconductors, and the operating temperature is 20 Kelvin. And the armature current density, we varied the armature current density to see which one is best, and then we fix the field current and the other field and shield current density. So these are the questions we have, like is that active magnetic shield is helping for wind turbine application, or can we go up to 10 Tesla? Is that possible? Or is it going to reduce the weight? And how much will be the AC losses when we go for this design? So this is the GIF showing that how this is going to look like. So the armature is fixed in the middle, and the field and shield will be rotating. This is the architecture. And this is the MgB2 wire. You can see that each of these black spots are the superconducting elements. And then this is the copper alloy that's embedded on it. So you can see that the wires are very small, 0.2 millimeter. And these are some of the parameters of the chosen superconductor. So, but what is the first challenge we have is the critical current density. For example, even though I say that we can push more current, but it's depend on the applied electric field. For example, if you increase the electric field density, then we can't push more current through the conductor. So you can see that if we have 2 Tesla, we can apply around 2000, and if we go to like 6 Tesla, then it will come to even very low current density. So then obviously the first question is that obviously we can't go for a higher design because the current density is going down with the flux density. So for example, here I have a electromagnetic design. You can see that in these regions the flux density is very high. What does that mean? Then I need to check that what is the flux density in that, and I need to go through this graph to see that whether I am in the safety margin. So for example, if the flux density is very high and if I push more current, then it will lose its superconducting property, and then we will be in trouble. So what I do for that, what I do is that I check in all these conductor, the critical places, to see what are the electric field, and I always guarantee that I am below the margin to push the current. So for example, if it is 20 Kelvin, if I am operating my AC in 20 Kelvin, and if my field is 2 Tesla, and I can go up to 200 amperes per millimeter square. But if the field is now increased to 3 Tesla, then I can only push 113 amperes per millimeter square. So I can't push, because this is the superconducting property. So for example, what will happen is that if you push more current, so for example, there are 3 curves that define the superconducting region. So one is the field, and the other one is the current, and the other one is the temperature. For example, if I am operating at 10 Kelvin, then I can push more current at more field. So if I go like 25 Kelvin, then my current and field density will go down. So this is the region that define that you have to operate below that to have the superconducting property. If you go below that, then it will lose the superconducting property and become a normal conductor. So for example, this is my my safety margin. For example, I want to have the armature current to be 0.5 of the critical current, so 50% of the critical current. And then the field current, I go for 75% of the field current. So as I explained that, these are the limits I have. For example, if I set to 2 Tesla, I can go up to only 200 amperes per millimeter square. And I have to make sure the armature current is, whatever the active field I have to evaluate the critical current density, and I need to make sure my armature current is below the 50%. Then we have the AC losses. The AC losses are similar to the hysteresis losses we see in the core. So the same kind of losses. For example, I have the penetration field that's defined that this is the field that start to penetrating the superconductor. Then I have the couple of losses, hysteresis losses and eddy current losses, and then coupling losses and transport current losses. These are the losses. All these losses only come when we go for alternating current and alternating field. If it is a DC current and DC field, no losses. For example, in the field coil, there is no losses because the field is not varying and the current is DC current. But these all losses only will come to an armature where the field is varying and I'm going to apply a varying current. So alternating current and alternating field. So I need to evaluate all these losses, and then we need to budget our cooling to extract all those heat that generated in the armature. So these analytical models, they are evaluated at low field and low frequency, but we are currently in the process of testing them for our operating region of our machines. So here I have a couple of pictures to explain that what does this mean to us. So for example, here I increase up to 10 Tesla, and these frequencies are very low. This is the wind turbine application, and you can see that the losses per watt per centimeter cube is very small, like 0.12 watt per centimeter cube. But if you go for a very high frequency like 2.5 megawatt motor, we are designing for Cheetah project. What will happen is that if you increase the flux density, the losses will go crazy, like 2 kilowatt. But for wind turbine, because the frequency is very low, we can still get away with the losses. So I just changed to see from 0 to 1 Tesla and see that what is the losses look like in a low field. So you can still see that this one is like 0.025, but this one is around 25 watt for a high frequency design. So why I am comparing this one? These are the design space we were looking at: 10 RPM and some pole count like 10, 20, 40, 50 pole counts. But here we were looking at 4,500 RPM and with these pole counts. So here the frequency is very high. Here the frequency is low. And if you it shows that if we go for a like this design, we have to go for a low field, but here we can go up to high field. So I have some design results so that where we are actually coming. What are the loss components? You can see that for a low frequency application, the highest loss is coming from the hysteresis losses. But when we go for a high frequency design, the highest loss is coming from the coupling losses. So different components affect in these two different schemes. So, and then what we are seeing, the another one, for this one, we can go for a very low field design because of the rate of change is decreasing here. So we can go, but then the weight will go very high. But here, we can't go for a low field design. So that's one of the point here. So here I have, so what I did is this, each point I have here is the sum of the motors we designed. And then I plotted with the field that we have here. So what it is showing that, so this is, I have the total losses in the machine, is this colored here. So what is this saying? That if I am targeting to be the losses to be less than 1 kilowatt in the armature winding. So it shows that I have only these regions that I can design my motor from like 0.8 to 1 Tesla. I can increase these losses to high, because if I increase the field density, what happening is the losses going very high. So it's not good. We can't go for this area. Here, even low field only we can go for design. But even though the magnetic loading is very low, but the advantage is that we are increasing our electrical loading by pushing the current in the armature winding. So for wind turbine, we can go from 0.8 to 1 Tesla air gap field density, but electric propulsion we can go up to only 0.64 to 0.6 Tesla. So how do we minimize our losses? So this is our optimization. We use a genetic algorithm based optimization. So these are, we design all of our parameters to be optimized. For example, the armature radius and the armature conductor area and the field conduct area and shield conduct area. All of the machine parameters we choose to be variable. And then we put a range to explore where our machine is going to be there. So how we design, for genetic algorithm will generate first the initial population, and we will go ahead and design the machine in Flux software, and then we do electromagnetic analysis, and we bring the torque and the axial length, and then we feed back into an analytical model to evaluate AC losses, and then we set an outside field flux density to be less than 50 millitesla, and then we put some constraint on the machine, like the radius would be this one and the length would be less than this one, and then we calculated the losses and the weight, and then feed back to the genetic algorithm to choose our new generators. So here I have some results. So what are the learning here is that so we estimated the AC losses in the axial length as well as in the end winding, and then I only consider weight as the active mass. That means the superconducting weight as well as only the copper weight. Because if you really consider all the weight, then we have to consider like all the other metal parts that we put on the machine. But I didn't calculate all those things there. This is the result I got. So what it is saying that, so this is the 10-pole design, and this is the 20-pole design, and I have 30-pole design and 40-pole design. So what it is saying that if we go for a low-pole machine, then the losses are going low, but the weight is going high. But if we go for a high-pole machine, then losses are going high, but weight is going low. So, but our critical challenge here is to minimize the loss. So so we need to go for a low pole design, even though the weight is very high. So I just plotted, I just magnified this area where I'm looking at to be 1500 watt and then 15 ton. So you can see that the different every motor, every point here is one design of a motor. So it shows that different pole count how they are in the. So and also so what we learned that is if we want to minimize the losses, so we have to go for a like low pole machine, but we can't even go. We can go even below that for like 4 pole, 2 pole, then the weight will go even higher. So and then I come back to see that, I mean, is that beneficial to go for an active shield design? So it shows that when we when we go for a design, so these are the design with significant ion shield. You can see that the weight is very high, but these are the design with significant without significant ion shield. So that's mean that the weight are going low. So actually the active shield design is actually minimizing the weight very. They are decreasing the weight significantly. You can see that here. This shows the ion shield thickness and then the active component weight. So these designs are corresponding to see that this ion shield is very small and the weight is very low. So the ion shield designs are really contributing to decrease the weight significantly. So that's, but then what are the parameters affecting the AC losses? The AC losses are affected by the air gap field density and the stack length of the machine. These are the two parameters that heavily affecting the AC losses. So here I have a comparison of 3 different extreme design. One is the lowest weight. So I can go ahead and design a 2.8 ton. It's a very lowest design, but the losses is very high. And you can see that when we go for a low weight, there's no ion shield. Because our optimization algorithm, we choose such a way that it can evolve towards the active shield design, or it can evolve towards ion shield design. So it's a freedom to go for whatever the design is better. So what we end up having is the design have combination of ion shield and the active shield. So these are the design that came to be an optimal design. Why I choose is an optimal design, because if you go for this one, the weight is very high, but the lower loss is low. But here we can have a reasonable weight with a reasonable loss. So you can see that the outer diameter is within the limit, and then we can look at the axial length. So lowest AC loss is axial length is very high, but for the optimal design we choose around 2.49. So it's good to look at the volume of the machine versus the losses too. So and then I have a 10-pole design also. I comparison of the 10-pole design, and you can we can also see here. So we can go for a very low weight design with these losses, or we can go for a high weight design with these losses. I forgot to change the numbers. So here is the numbers for the weight. We can go for like 470 watt, 777 watt, or we can go for 1135 watt, or this is the optimal design. I choose 618 watt losses. So here I have a like picture of how this machine is going to look like, and then this is the EM design shows that. So here I have the calculation to show that what would be the efficiency, what would be the total weight of the machine. So the design I considered is 618 watt, and then it's 11.3 ton, and then the axial length is 2.45 meter, and the diameter is 4.29 meter. So here I calculated how much required cryogenic power I need. For example, even though the loss is 618 watt, but to remove this 618 watt, we need to put more power into the cryogenic system to remove it. For example, because we need to remove this power at 20 Kelvin. So we are trying to remove the power at 20 Kelvin. So the power we need to put into the cryogenic system is 37 kilowatt to remove 618 watt. That's why we want to minimize the losses in the machine. So if I put all these numbers here, so what is the efficiency we were talking about is around 99.6%, which is including all the power we are putting to a cryogenic system. So even if I overestimate this one, we can see that we have a lot of margin to go a 99% efficiency machine design. then I'm trying to estimate the weight. So 11.3 ton only for the active mass. This means the ion sealed and the superconducting. If I include a 200% of more weight, and then if I then also we calculate that to remove 1.5 watt, we need a 10 kilogram of cryogenic system weight. If I include that, you can see that we were around 38 ton. That is well below the typical conventional machine. So you can see that we are going for a fully superconducting machine, we can go for a very high efficiency machine and with a low weight design. So that is the main reason why we were exploring the fully superconducting machine for wind turbine application. So what are the conclusion here? That fully superconducting machines are attractive for like 10, 12 megawatt wind turbines, and then armature winding AC losses and associated cryogen system weight are significant challenges, and then relative low field, low pole count designs preferred. So that's what we are looking at, 10 pole design with a low field, and then ironwork weights dominates in passively sealed. So that's why we were looking active shielded design, so we can remove the weight from the machine. So one of the challenges is that all our machine calculation is not, we just estimating only using some simple model to estimate the weight. So we have to at least design very well in CAD models of our machine. To increase the technology readiness level, we were trying to validate the AC loss models that we used in the machine design space. So I mean, all of these studies so far, what I did is I was trying to minimize the AC losses and weight. So now I'm trying to look at how if I try to minimize the AC losses and the cost of the machine to look how it's going to look. That's all my talk. If you have any questions.
How does the cost of the cryogenics compare to the cost of the motor and some of the other materials there? Like, I mean, you talked about how you had to add so much cryogenics, like, you know, from a power perspective, but from a cost perspective, how does that system scale up compared to maybe scaling the size of your motor?
I haven't looked into that the exact cost, but for example, when I went to like last month for a conference, then I mean, for example, the off-the-shelf cryogenic system to like extract 40 watt, it's cost around $40,000. But this system we need like liquid cryogen coolers and then the tanks, and then we just send the liquid coolant inside the machine and then we'll take back. I think it's also very costly, but I don't know the figures of if we want like 1 kilowatt cryogenic cooling, how much it will cost. I think I need to look into that. Yes.
Thank you very much for a good presentation. I'm curious about a few things. So can you discuss the impact of the sensitivity for some of your optimization? Because you're in a unique space where you have a lot of these discrete values coupled with continuous values. So can you discuss perhaps how you did sorting for machines that are not possible, and or if you, for the continuous values, have maybe a 5% change, how far away does it go from the optimal path? So if you go back to some of those curves, have you investigated some of those questions? Have you thought?
That's a good question. For example, here.
Yeah. Because you're not showing all your other designs. You know,
Yeah.
Because this is like have all on the page. So like if I move 5% on one of those continuous values while staying within the same discrete choices, how far away do I get from that curve? I'm just curious.
Yeah, I need to look into that.
Okay.
But all of the parameters we were looking at is continuous. For example, here.
Oh, really?
Yeah. So I mean, all of these are continuous, but only the discrete values, the pole pairs.
Yeah.
Like,
Okay. Yeah. That's what I meant.
Yeah.
Well, so did you see, because you went through a lot of designs, so for those discrete values, do you see some generalization in terms of trends? Maybe I missed that part. So if you take pole pair out and maybe operational frequency out, what was an insight that you took away, or maybe you're still searching?
Yeah.
There's a general takeaway?
The general takeaway, for example, that's what I was looking at this one. For example, where the air gap field stands for all of this design.
Yeah.
So you can see that it's only between 0.8 and like 1.2. It's never going beyond that. Even if we go beyond that, the total losses in the machine is going very crazy. So we can't go and design this. But it's and also I look at that. What would be the axial length? How much is the axial length varying? How much the diameter varying? But yeah, I need to look into the different parameters and how they are affecting. Still, I need to look into that. But most of the concern we had is what is the air gap field density and what is the armature current. So those are the two parameters we were.
But if you could help me understand the plot on the left, because I apologize for poor eyesight, I can't really see. What can you explain what those curves are? I understand are those different pole pairs or what?
Yeah, these are different pole pairs. So this one is from 10, 20, 30, 40 pole pairs.
Okay.
And these lines are, the solid lines are the analytical model results. So for example, if I increase the field, how much the watt per centimeter cube is going to look around. And this, all the dots I have here is the actual machine design. And I calculated watt per centimeter cube in the actual armature winding. And I plotted both of them together to see where they are standing. So that's.
So on your last slide, you talked about costs.
Mm-hmm.
So making that 40, if I understood what you just said, that 40 pole pair device, what is the difference in manufacturing cost? Do you have like an order of magnitude? Like, because you built that NASA machine.
Yeah.
So if it had fewer pole pairs, would you have been happier?
I didn't look.
You didn't build it. You just
Yeah, but
said,
the manufacturing, we need to. Yeah, I mean, when I say cost, these are only the material cost.
Oh, material cost.
Yeah.
Okay, not the manufacturing cost.
No.
Oh.
Yeah.
Cost of graduate student is not that.
Okay.
Yeah, but building this one will be a
That's
different
very
story.
interesting.
Yeah.
Thank you.
Another question. So I remember there was a slide you mentioned about the hysteresis loss,
Mm-hmm.
and it turns out the lower frequency machine has lower hysteresis loss.
Yes.
Can you explain like the reason why? Because like one of the things with hysteresis loss, the more you traverse along the pH curve, the more loss it will incur. It means that if you have higher frequency, it's natural to think that it will have more hysteresis loss.
Okay, yeah, that's one of the reasons for that. For you see that here we have BM and F. So you can see that when the frequency goes high, the high hysteresis losses will go high, right?
Yeah.
But then we have another term JC here. So what happens is that JC is dependent on the critical current is dependent on the field. So if you go and look at my previous slide, yeah, this one. So what happens is that when the field goes high, the critical current is becoming low. So if I am applying 6 Tesla, then I cannot put lot of currents into that one. So that's the reason. So I always assume that my armature current is 50% of the critical current. So now go back to these slides. What we happening here is that when I increase the frequency, of course the losses going high, but because of the JC, the losses coming low. So because now the JC is very low because the field is very high, but because the JC I can put is very low.
So there should be a point that you have the minimum hysteresis, like if you combine the frequency and the current.
Yeah.
You see, like I guess that there was a point you have the minimum loss.
Minimum losses.
Yeah.
But then what will happen is that that's what I said in the other. But these are the square of the frequency. These losses. So what will happen is that they will try to dominate if we go for a high frequency design, and then these are dominating, and the low frequency domain these are dominating.
Yeah.
And then I understand that there would be a point that where it's trying to be minimum for both of them, right? Yeah.
Any more questions? Because I have one more.
I have a question. We can take turns.
Oh.
You want to go to slide 16? I had a question about that.
Is there any way to go quickly? I don't know. No.
It would be time to go
Yeah.
for that. For 1 sec, let me find which one it was. Actually, can you go to the next slide?
I think these values are wrong. I couldn't change them.
For the air gap flux density here,
Mm-hmm.
it looks like your lowest weight and lowest AC loss are both lower than your optimal design. Is that a pattern you've seen where the air gap flux density is sort of highest in the middle of your design space?
Yeah, it's happened. I mean, I looked at this one. It's like this, but it's not for the other one.
Yeah.
So yeah, it's not for the other one. But it was like this for this one. I need to like investigate that one more. I think.
I
Yeah.
was going to ask, do you think this is actual phenomena? Like, is that actually how a true good optimization would result, or is it result of not quite converged optimization? It sounds like you just need to look into it and figure out.
I need to look into it and figure out.
Cool.
The other question, can you comment on how does active shielding work, and what is the reason makes the active shielding reduce the weight of the machine?
Yeah. So the only reason we have active shield is to contain the flux within the machine. Other than that, because in the conventional machine we use iron core to increase the flux density, right? But because we have superconducting field coils, we can go for a desired field without iron. So we don't need iron because we can reach our desired flux density without the iron shield or iron core. Okay, but only the reason we put iron shield around the machine to contain the flux within the machine for a safety reason. But there's no other reason to have a shield coil here, because actually if you put shield coil, it will reduce the flux density inside the air gap field. That's what is going to happen. But what will happen is that because we are putting the shield coil, then we can reduce the outside flux density to the safety margin. So that's the reason.
Back up a step and explain what shield coil is.
So the shield coil is that, okay, so this is an opposite, is going to create an opposite field here to like contain the flux without going outside the machine. That's the only that reason that we are having that shield coil here, and it's quite useful for like electric propulsion design because people are around the machine, and then that's the reason we put a shield coil around the machine to contain the flux within the machine. Yeah.
Is that shield coil also superconducting, or is that connected?
It's also superconducting.
Did you say that in the optimal design there's both shield coils and iron shield?
Yeah.
So why is there both types of shielding and not just one?
Yeah, because one of the reason I was thinking is that, for example, if we go for only shield coil, what happens is that we have more flux here because we are trying to contain all the flux using only the field coil, only the shield coil. So it's because, and then I have a limit that I cannot go beyond 2 Tesla at the field coils, because if I go for more than 2 Tesla at these points, then I cannot push 200 amperes per millimeter square. So that's what one of the reasons that why we are choosing with the shield coil and the coil. And if you go for, but one of the other reason that if you go for only shield coil, what happening is that the losses is going very high. So by my design, I was choosing to minimize the losses. So that's why we are coming up the design that have the iron core and the shield coil, because when you have iron core, then it's also contributing to increase the flux density. So then we don't need to push much current. So we need a small coil, field coils is enough to create flux inside the machine. That's just one of the reasons.
I guess one last question. Why are you using a genetic algorithm for your optimization rather than just a gradient descent-based method?
So because one of these, the nonlinearity we have here in the iron region, and we are looking around very high field. So that's one of the reasons that we go to a finite element method and then getting the result. So it's a nonlinear. I cannot model as like using equation. So that's one of the reasons we are using genetic algorithm.
gradient
But-
descent, I mean, you can incorporate that in the gradient descent algorithm.
Yeah. Maybe the reason we choose is that because the previous studies, the NASA Learn program also, they used the genetic algorithm, and then I continued that to explore this one. But if maybe it's the gradient-based method also will work.
I guess one way to maybe see if that's worth it is you already have all the solutions out there for your Pareto problems, and you can look at your continuous variables and see that they're mostly continuous
Okay.
in the solution space. Then that would suggest gradient descent will probably be just fine. But if they're all over the place, then
Oh,
genetic
okay.
algorithm.
Okay, it's not like going. Oh, okay. Okay.
Or it may just point out that there's more than one on your optimal solutions are very close together if they kind of bounce back and forth between values.
It will
Okay.
also help you understand what you pointed out to them, the segmentation of which loss dominates where. You
Okay.
can build a multi-dimensional surface understanding of that. We can talk more afterwards.
Okay.
The number of parameters influence and like how long it takes to compute one influence what makes sense.
Possibly. I don't think you're using that many parameters that would influence the decision, but that's about the one that define optimization. Technically speaking, so.
Maybe we need to compare both of them, right? I think that's good.
Local how to these solution, is there a way we can judge that? Because depending on when you start the initial condition, it may just convert to a local flow.
So some of that depends on
That's how you define the
how much and the nature of the problem. So that's where you're right. Like if you have a lot of nonlinearities, and especially in the discontinuities, then gradient is not. But when everything's completely variable like this, I don't think you would get any. It seems like you'd be weird if you're really getting any discontinuities in your design space. I would think gradient descent be an option.
Yeah. That's a good point. Yeah.
Yeah, there's a really good paper out of a school in Canada by, his name is Dr. Stuper. So we can talk more afterwards. He does this for inductor design, which has all the same nonlinear properties, but he's using gradient-based descent methods with multi-objective output.
Okay.
Is it faster than a genetic algorithm?
I don't know. It converges.
Yeah. I mean, if it is convergent. Yeah. I mean, it's depend on timing is
Just tell
another.
Dr. Haran to buy a faster GPU. Little workstation.
Yeah.
Or some undergrads to crank them. Thanks.
Thank you very much.